As I said in the previous video, this particular page right here is going to serve as something of an outline for us. Notice again that we have classified lipids into two categories: those that are amphipathic, that we call polar lipids, and those that are pretty much all nonpolar and completely insoluble in water. I also pointed out that one of the key functions of lipids is to serve as fuel for our body. And I'm going to start there. Let's focus on, in this video, fatty acids, which are one of the basic fuels that we use for long-term energy storage. There's 6 of them that we want to know, but before we get to that, let's go on and look at the actual chemistry of fatty acids. So fatty acids are pretty simple. They are just long carbon chains with a carboxylic acid at the end. And they're not typically branched, and they can be single bonds or double bonds, as we'll talk about later. Now I've drawn out a fatty acid with 16 carbons. And to number fatty acids, which is an important skill, we always start at the carbon that is the carboxylic acid, and we simply count out. Like I said, it's unbranched, so it's pretty easy. We just go out to 16 carbons. This particular fatty acid is one of the most important in our body. I would call it maybe the glucose of the fatty acids, and it's called palmitic acid. I suppose it's found in palm oil, and that's where it comes up with the name. Now, a couple things about fatty acids. First of all, we can tell you that the number of carbons in fatty acids is typically an even number. Not always, but usually it is. And the numbers that we're going to be most interested in is going to be 12, 14, 16, 18, and maybe 20 we'll throw in there as well. These are real typical fatty acids, and like I said, they tend to be even numbers. That's another issue. It comes from the fact that they're made from units of 2. So let's move on and point out that drawing out a fatty acid, which you will have to do from time to time, is not that hard, but if you have to write out all the atoms, it just takes a lot of extra energy and work. It's better to simply draw out palmitic acid with a stick structure like we have shown here. That makes it so it's easier for me to grade, it's easier for you to draw, and you don't have to worry about whether you get the number of hydrogens right. They're implicit. So I prefer this structure, but I would also point out, as we learned in previous units, that a carboxylic acid is not typically going to be a carboxylic acid in the human body. We would expect that a carboxylic acid with a pKa in the range of 2 to 4 or 2 to 5 at neutral pH will be in the basic form, that is, the carboxylate form. So the next thing I would suggest you do is always draw fatty acids out as the base form. And in this case, we would call this palmitate. It's not really a fatty acid anymore. It's a carboxylate version of that. Now, there's one more thing that we can do to make this even easier, and that is we have a systematic number nomenclature for fatty acids, and it's really pretty easy. First of all, we write down the number of carbons, in this case 16. We put a colon, and then we write the number of double bonds, that is, double bonds between carbons. In this case, there are no double bonds between carbons, so the palmitate is known as 16:0. Now, this and others like it are called saturated fats, so let's make a note of that, or saturated fatty acids. Maybe you've heard that term, saturated fats, unsaturated fats, polyunsaturated fats. These have some implication for nutrition, and you'll certainly hear about them in other classes. But at this point, that's it for fatty acids, at least for the saturated fatty acids. It's pretty simple, and we're ready to move on to unsaturated fatty acids. So let's do so, moving to the bottom of the page here, and I'll just put over here again, unsaturated. There's an open question here. When we say saturated or unsaturated, the question is saturated with what? Or unsaturated with what? Well, we'll come back to that in a little bit. But saturated and unsaturated means the presence of double bonds. And unsaturated means actually having double bonds. Saturated means not having double bonds. So I'd like to tell you a little bit about how these double bonds are laid out in fatty acids. And the first thing I want to tell you is that they are typically in the human body in a cis form. I hope you remember the idea of cis and trans from organic chemistry with regard to double bonds, alkenes that is. It simply means that when you have a double bond between two carbons, the next carbons in the chain are on the same side of that double bond as opposed to opposite side, which would be trans. Now you may have also heard of trans fats, and those are what they sound like. They are fats that have trans double bonds rather than cis double bonds. But those are typically artificially made in an industrial food processing way, and the ones that we have naturally are tending to be cis double bonds. Okay, so how do we deal with this? Well, let's talk about a fat that we might call oleate. It's actually oleic acid, but remember, I'm going to change it to oleate because we would expect it to be deprotonated on the carboxylic acid. So that's the first thing I'm going to do is take away that H and make it an O minus. Here's how we do it. When we have a double bond, we are going to use a delta for indicating the position of that. So if we had a delta N, N being a number, that would indicate a double bond between carbon N and N plus 1, the next one in line. So here's how it works out. What we typically see is something like, for oleic acid or oleate, it would be 18:1 with a superscript delta 9 telling you the position of the one double bond. Go ahead and draw out this fatty acid, pause the video, and we'll see how you do. Okay, let's go ahead and first consider that we've got to draw 18 carbons, one double bond, and that has to be between carbon number 9 and 10. Sounds pretty easy, but people make a common mistake here, and I want to take you through it. The key is not to draw all 18 carbons first. Let me show you how I think about this. Carbon number 1 is the carboxylate, then we go to 2, 3, 4, 5, 6, 7, 8, 9. Now pause for a second. Remember, there's going to be a double bond between 9 and 10. And remember, it's a cis double bond. So once I draw a 10, I need to draw 11 on the same side as the other carbon. So that's 11, 12, 13, 14, 15, 16, 17, 18. This is what oleate looks like, and I will take off a small point if you draw it with a trans double bond instead of a cis double bond. Okay, so we're almost done. I would like to point out that the double bonds in fatty acids affect melting point, and this is a point we'll talk about in the next video. Double bonds lower the melting point. It's simply this. When double bonds are introduced, the double bond causes a kink in the fatty acid. That causes the fatty acids not able to pack together as well. And if they can't pack together, they're going to be much easier to loosen up from solid to liquid when we raise the heat. So double bonds lower the melting temperature, tend to make them more liquid.